than to choose, a little pick and then run across the limitations at the wrong time. So this is why we've chosen this for now. So I'm going to explain a bit about how the spoofing works. Now, if you take a look at this diagram here, first I have to say I have blatantly stolen this from the RFID handbook by Klaus Finkenzeller. It's a great book if you want to learn about RFID. But what you're going to notice, you're going to have a large peak in the middle. If this was the kind of RFID that we're using, then this peak would be at 13.56 megahertz. Now, when the tag produces a response, the way that it works is it flips on and off something called a load modulation resistor. So basically, the reader and the tag are making what's called an inductive coupling. It's almost just like kind of an electromagnetic coupling, so that when this resistor goes on and off, the reader can just feel it. And the way that it works is then it produces these things called sidebands that are a small number of kilohertz on either side of this carrier frequency. And it's actually the sidebands, it's actually these two little peaks that contain the tag response, that contain the actual information. And it's the challenge and it's the task of the reader to filter out this really massive carrier signal. Because remember, this is just noise. This is a signal that the reader is producing, so it already knows, exactly what information is there. But just it needs to have pretty sophisticated circuitry to pluck out these two little tiny sidebands. So, and as I mentioned before, there's a 90 decibel difference between the strength of this carrier signal and the strength of these little tiny sidebands. So, this is what the RFID Guardian does. You're going to notice this picture is a little different. First, ignore everything that's on like these sides of the sidebands because, well, that's just noise, and that's what happens in the real world. But what you're going to see is that in the middle of this picture here at 13.56 megahertz, this is the carrier signal. But on either side of the carrier signal, there are just these massive sidebands. In fact, the sideband on the left side here is actually bigger than the carrier signal itself. So what are we doing? When we first decided how we wanted to emulate a tag, we thought, gee, maybe we can just, also have a little resistor and flip that on and off in time with the, with the standard. But if we did that, we would be reacting passively just like a tag, and we would have the same range limitations as a tag. But instead, what we decided to do is we are actually making an active transmitter that just transmits these two sideband frequencies actively. And basically, the only thing that this is limited by are relevant regulations about RF emissions. So, in generating these massive sidebands, at least with version, well, we got slightly better performance from version 1 than version 2. We're actually optimizing it now with version 3. But the point is, the largest distance that I saw the RFID Guardian work was almost a meter. So the point is we can transmit these tag responses at basically the limits of the range of how far away we can hear the reader. Whereas, indeed, a tag would just be limited to the 10 centimeters or, maybe 30 centimeters, if you're lucky, if we did it passively. Of course, once we have these sideband frequencies, I should add, we also had to implement our own ISO stacks. Because then, of course, once you just have, the raw data that's being transmitted, then, of course, we have to make bits out of it, and we have to make frames out of it, and we have to, on the higher level, actually be able to respond with real answers. So all of this was very well dictated by the ISO standard, and for the rest, it was just a bit of programming to get it to respond within the appropriate time constraints and that kind of stuff. So jamming. So how does the jamming work? Now, naturally, if you just put out random noise all the time, this would work, but that wouldn't be very desirable for having sort of a really selective granular jamming device. So the way that it works, at least with the particular ISO standard, is when it's doing inventory queries and it's doing anti-collision, it has 16 time slots. So the way that it works is during anti-collision, each of the tags, almost pseudo-randomly, it almost seems pseudo-random, will choose one out of these 16 time slots in which the tag wants to respond. But the point is, this is something we can calculate. This is deterministic. We know exactly how the algorithm works because this is well specified in the standard. So the actual way the tags choose a time slot is they'll do an XOR of their tag ID along with something called an anti-collision mask, which is a value that is dictated by the reader, which changes during every round of anti-collision. And essentially, in such a way, each tag can sort of probabilistically choose one out of the 16 time slots, and you sort of hope that, with enough rounds of anti-collision, eventually all of the tags will be able to get their responses back, so they're not all sort of talking over each other. So in this example here, you can see if we have 4 tags, let's say that tag 1 would be talking in time slot 5, tag 2 would be talking in time slot 9, tag 3 would be talking in time slot 2, and tag 4 would also be talking in time slot 5. So if this was the first round of anti-collision, what would naturally happen would be that the tag 3 talking in time slot 2 would be able to get its response back because there's no collisions. So, it's basically sending its UID, its tag ID, within the constraints of this time slot, and that's how it's getting its info back. But you would see that tag 1 and tag 4, because they both chose time slot 5, are going to interfere with each other, and they're going to talk at the same time, and the response is going to be garbled, so you won't be able to understand it. So in the case of with tag 1 and tag 4, what would happen is the reader would then say, okay, let's go to the next round of anti-collision. It changes this anti-collision mask, and then you hope in the next round that tag 1 and tag 4 now are going to choose different time slots. So now, once again, in this next round, they'll be able to get their individual answers back. Now with the RFID Guardian, we know that in round 1, tag 2, let's say tag 2 is a tag we're protecting. Let's say it's my passport. Okay? Now I know that tag 2 is going to speak in time slot 9, because I can calculate this. So we send out random noise, and that's all it is, random noise, during time slot 9. Now, the reader says, okay, I heard there was a collision. Let's go to the next round of anti-collision now. Well, once again, what we do is we calculate, okay, in this next round of anti-collision, I know that this tag is going to speak in, time slot 15. And the point is, we keep injecting random noise into the single time slot where we know the tag is going to be speaking, and the reader goes through 16 rounds of anti-collision, and then it gives up. So, and when it gives up, sometimes it'll give a CRC error. Sometimes the reader doesn't even notice. It actually just depends on how the back-end software is written, whether it'll notice that there's a problem or not. And that is actually how the selective jamming works, as we demonstrated in a video. In such a way, the chances are just, 6 to the 16 that you would have another tag that would respond exactly in that same sequence of time slots. So the point is, in such a way, you can really granularly say, I'm going to block this tag and that tag, but I'm going to let everything else be able to speak like it's supposed to. So, all right, of course, as hackers, if you want to make a real pain in the butt out of yourselves, you can understand why spoofing and jamming would be useful. But also for consumers, we thought that spoofing and jamming would actually make really interesting primitives for building something that almost resembles an RFID firewall. Now think about this. If you have a firewall for a network, if you have a packet filter, the way that it works is it will analyze incoming packets. It will be able to look at the meaning of these packets. So what exactly is this particular packet attempting to do? Is it setting up a connection, breaking it, trying to send some data? And it can actually make decisions based upon who is sending this packet, what port is it targeting, what flags does it have, and it can actually decide whether or not to block it, to filter it, or just to let it go. And this is the basic idea behind the RFID Guardian. Right now, RFID activity that's going on around us is not very transparent. I mean, or actually, maybe I should say it's too transparent. The point is it's radio waves, and as being a consumer, we can't see it. I mean, unless, of course, you have one of these nice wristbands with the little LED. But the only thing that will show you is that you're in a 13.56 megahertz field. But it won't tell you, for example, this particular reader is doing an inventory query, or this particular reader is trying to target your passport and get information from it. So the way that the Guardian works is, okay, it's like a firewall. You could use it to protect either people or fixed locations. So let's say I'd have one of these devices. I'd kind of put it on my belt. And if it has an operational range of about 1 meter, like I told you before, what you're going to get is sort of like a little zone of privacy, basically like from your belt upwards and downwards. Now, if I have an RFID tag on my jacket, and I put my jacket down on a chair and walk away, my jacket is now not protected. But that's the rules of the game. You have to understand. This is localized, and you have to understand if you have one of these devices within a particular range, you're going to get this protection. If I decide I want to protect, for example, my living room, then maybe I can put one of these things there with the understanding that just in this one area, I'll be able to control the RFID activity going on. Same thing if you're at border control at an airport and you want to make sure there's no unauthorized RFID readers just in that little area where they're scanning your passports. Take one of these things, put it in that area, and it can monitor and control the RFID traffic just in that localized area. So, but what are some of the main functions that we envision with this RFID Guardian? Well, the first thing that it's useful for is auditing. So I was talking before about packet filters. I mean, something that we like to do a lot is look at the network traffic. I mean, perhaps try and analyze it for statistics, how much bandwidth is going on. But also, I mean, is anybody doing anything they're not supposed to be doing? I mean, you know, should I change my firewall rules? I mean, maybe you want to hang an intrusion detection system on there. I mean, the point is that right now with RFID, there is no way to really efficiently monitor the RFID traffic. Now, what you can do with the Guardian is because it can take RFID queries, I mean, just, you know, receive them, demodulate them, decode them, get the information out. We're able to say that, for example, you know, at 12:35, there was a reader that was attempting to read some tags that belonged to me. Now, the point is, if they want to, for example, pass privacy legislation saying that a store needs to signpost what RFID queries that they do if they're targeting RFID tags belonging to an individual, the point is, as a consumer, how do you have a way of knowing that they're doing the right thing? I mean, how do you actually check to make sure that they're not breaking the rules? Now, if you have one of these devices, what you can do is, with all of the queries that are coming in, you can actually just filter out just, you know, the queries that are relevant to some small subset of tags that belong to you. And if enough, I mean, we assume in the first place, you know, normal people aren't going to have such a device. But if you have a couple of gearheads, you know, because, you know, this is, of course, the initial group of people that would want one of these things. If you have enough geeks that have one of these devices and then notice that around the time that they were in this department store, someone was scanning tags that would belong to them, then they now have kind of a proof that collectively some of them could actually go to the authorities or the Chamber of Commerce and complain. So it gives consumers sort of a legal recourse that they might not have had before. Another thing that could also potentially be useful is if you have, let's say that I leave my house first thing in the morning and I have one RFID tag with me. Now let's say I return home at the end of the day and I have 2 tags. Where did that tag come from? And how, as a consumer, do I know when that tag was added? And perhaps then you can correlate it back to where. If you can routinely or periodically scan to see what tags do I have now that are near me, that are geographically near me, you can figure out, depending on how often you scan, exactly when you're acquiring new tags. And if you're not acquiring it through a way that you would expect, once again, this gives you sort of more knowledge as a consumer that you wouldn't have had before. Key management. So earlier on, I mentioned kill keys with EPC global tags, sleep and wake modes. Some RFID tags have